Now we're going to be learning about the bitwise operators. And when we talk about bitwise operators, these are operators that allow us perform operations at the binary level, that is at the machine level. And we'll start by listing out the different types of bitwise operators. We'll have the bitwise AND operator. This is different from the logical AND, and the symbol is this. Then we'll have the bitwise OR operator, and we use the pipe symbol for the bitwise OR. The next one is the bitwise XOR operator, and we use the caret symbol for the bitwise XOR. Next, we'll have the bitwise left shift, and we use this symbol. We also have bitwise right shift, and for this we use the symbol. And finally, we'll have the bitwise NOT operator, and we use the symbol for the bitwise NOT operator. But before we get into the bitwise operators, let's have a little overview of the binary number system, or the number system in general. So we'll look at the number system. When we talk about number system, we're talking about counting, how we count. And we have what we call the decimal number system. Decimal number system is the regular way we count. We'll count starting from 0 to 9. The least digit is 0 and the highest digit is 9. So we'll count like 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 being the highest digit. When we get to 10, because we don't have a digit called 10, we're going to put 1 in front, then put 0. We'll continue like this until we get to 19. When we get to 19, then we'll change this digit. We'll add 1 to this digit, making it 2. We'll now have 2 and 0. We'll continue like that. So this is the decimal number system, or the denary number system. In fact, this is the natural way we count. Now, we have other number systems. We'll have the binary number system. This is zeros and ones. We'll count in zeros and 1. And typically, we'll start from 0. We'll count 1. Because we don't have 2 in the binary number system, we're going to have 0, and then we'll put 1 at the back of it. Then we'll continue. We'll have 1 and 1. The next digit is going to be 12. But because we don't have 2, we're going to have 0, and we'll carry the 1 and add it up to this 1. And this will give us 10. So we'll have 1 and 0, making it 100. The next one becomes 101. The next one becomes 110. It continues like this. We also have the octal number system. This is base 8 numbers. The highest digit is 7 and the smallest is 0. So we'll have 0, 1 all the way till 7. When we get to 7, we don't have 8. We'll have 1 and 0. We'll continue like this until we get to 1 and 7. Then we'll have 2 and 0. We'll continue till we get to 2 and 7. And we have 3 and 0. So this is the octal number system. Then another one is the hexadecimal number system. And this one is base 16 numbers. So counts starting from 0 all the way to 9. And then for the 10, we'll have A. 11, we'll have B, all the way till we'll get to F. And then we'll have 10. We'll continue like this. So this is base 16. So let's get back to our bitwise operators. When we perform bitwise operations, we're performing operations at the binary level. So let's start with the bitwise AND. And of course, the symbol is this. And we'll have num1 is equal to, let's put it as 5, and we'll have num2, which is equal to, let's have 6, and result is equal to num1. We'll put the bitwise AND operator and we'll have num2. So let's go ahead and print the result, then we'll explain what happened. So we'll have print result. So we'll run the program and we have 4. So how did we get to 4? To understand this, we need to get the equivalent values of these numbers in binary. And to do this, we're going to be using a function called bin. For us to get the binary equivalence of 5, I'm going to have print bin. Then I can put num1. So let's run it. So the binary equivalent of 5 is 101. So let's see the binary equivalent of 6. And for this, I'm going to copy this and paste it below, and I will change this to num2 and run the program. So this is the binary equivalence of 6. We have 101 and we have 110. When you're performing the bitwise AND operation, like I said before, the operation is performed at the binary level and it is done digit by digit. So let's look at this starting from the right. We have 1 here and we'll have 0 here. If you can remember how we performed our logical AND operation, I want you to see 1 as true and see 0 as false. When you have true and false, you are going to get false. So here we have 0, which is false. Now, let's get back to the second digit starting from the right. We'll have 0 here and we'll have 1 here. So this is false and true, which will give us 0 as well. Now, we'll look at these other digits. We'll have 1 and 1, which is like true and true, which will give us 1. So we'll have 100. If we convert this to the decimal number system or to integer, we're going to get 4. So this is how we came about 4. Or better still, we can have print and we'll have bin result. And we'll run the program. So you can see we have 100 as our output. So this is for the bitwise AND operation. Now let's look at the bitwise OR operator. So we have bitwise OR and we use the pipe symbol for the bitwise OR operation. And we have result is equal to num1 or num2, and we'll print our result. So this is print result. So let's go ahead and run the program, and for our output we have 7. So this is what happens in the background. First of all, let's see the binary equivalence of num1 and num2. So we'll have print bin num1, and we'll do the same thing for num2, which is this. We'll change this to 2, and we'll go ahead and print the binary equivalence of the result. So we'll have print bin result, and we'll run the program. So this is what we get as our result after the bitwise OR operation. But this is what happens in the background. We have 101 and we have 110. In this operation, we have 1 here, which is like true, and this one is like false. When you have true or false, you are going to get true. So have 1. And here we have 0 and 1. So we also have 1. And finally, we have 1 and 1, which is like true and true, and we have 1. So our output or our result is going to be 111, and you can see it here. We have 111, and of course in decimal number system it is equal to 7. So this is how we came about 7, which is 111. Now let's look at the bitwise XOR operator. And for the bitwise XOR operator, we use the caret symbol. So this is the symbol that we use. Now I'm going to change this to the bitwise XOR operator, and we'll run the program. And you can see we have 3, and the binary equivalence is 1, 1, which is 11. So this is what happens when we perform the bitwise XOR operation. We're starting from the right. So we'll have 1 here and we'll have 0 here. Because they are of opposing values, we're going to get 1. So we'll have 1, we'll have 0, so we'll have 1. For this, we'll have 0 and we'll have 1. We're going to get 1. This is the same as this, so we're going to get 0. If we had 0 here and 0 here, we'll still get 0. So we only get 1 if the values are of opposing values. So this is how we came about with 11, which is equivalent to 3. So this is for the bitwise XOR operation. Now let's look at the bitwise left shift and the bitwise right shift. And for this, we have bitwise left shift, and we use the symbol. And here we have num is equal to 8. And let's print the binary equivalence. And so we have print bin, we'll have num. Now we're going to be performing the shift. So we'll have result is equal to num, then we'll provide the shift, then we'll provide how many digits we want to shift. So let me have it as 1. So let's go ahead and print the result. So print result, and we'll also print the binary equivalence of the result. So we have print bin, we'll have result. Now let's run the program. From the output, you can see that 8 is equivalent to 1000 in binary. And after the shift, we have 16. And 16 is equivalent to this. So look at what happens. We have 1000 as the value of 8 in binary. So imagine that we have spaces like this. So what happens when we perform a shift? For instance, we are performing a shift by 1. We're performing 1 shift. It means shift it to the left once and add 1 0 at the right. So this is what happens. Assuming we're to perform shift 2, what it means is that we're going to shift it to the left 1 2 and then add 2 zeros in the front. So we'll have 1 2. So let's try it out. And we're going to have 2 here and run the program. If we run the program, you can see we now have 100,000 because we shifted it by 2. If we shift it by 3, we're going to end up with 1 million. So you can see we have 1 million. So this is for the bitwise left shift. Now let's look at the right shift. For the right shift, we use the symbol, and I'm going to change this to the right shift operator, and we'll run the program. As you can see, 1000 is equivalent to 8. And let's see what happens. What happens is that we have 1000 like this, and when you're performing a right shift, it's like you are pushing the digits to the right. So I'm shifting it 1 2 3, and then I'm going to remove 3 digits from the right. So we'll have 1 2 3. Now let's change this to 1. If we change this to 1, originally we have 1000. So this means we're going to shift it to the right once and then remove 1 digit from the right. So we'll have 100. So let's try it out. And from the output, you can see that we'll have 100. So this is for the bitwise right operation. Now let's look at the bitwise NOT operator. And here we have num is equal to 8, and we have result is equal to, I'll put the operator and then put num. So let's go ahead and print the result. So we'll have print result and we'll run it. And as you can see, we have -9. Now let's change this to 7 and we have -8. If we change this to 1, we're going to have -2. So, but the theory behind this is beyond the scope of the lesson. So far, we've looked at the operators that fall under the bitwise operators. We looked at the bitwise AND operator. We looked at the bitwise OR, the bitwise XOR, and we looked at how we can shift our digits using the bitwise left shift and the bitwise right shift. And we also looked at the bitwise NOT operator. As you progress in programming, you are going to appreciate these operators. But before we conclude this lesson, we looked at the bin function, which we use to get the binary equivalent of an integer or a natural number. We also have other functions like the hex, which we use to determine the hexadecimal equivalence. We also have the oct, which we use to determine the octal equivalence. For instance, we have num is equal to 22. Let me remove this. So if you want to get the binary equivalence of 22, you will have print bin num. I'm going to be removing this and we'll run the program. So this is the binary equivalence. Then if you want to get the octal equivalence, I'll simply copy this and change this to oct. And this will give us the octal equivalence, which is this. And as you can see in the binary, you can see the B here denoting binary. This is denoting octal. And if you want to get the hexadecimal equivalence, you use the hex function. So this is hex. And we'll run it. You can see the hexadecimal equivalent. You can see the X here representing hexadecimal. And this is where we're going to be concluding our lesson on operators in Python.